All right, that's my cue. Thanks everyone for coming. Hopefully it'll be an interesting day. You've all seen the description online, so without further ado, I'll get into it. Very briefly, the agenda for today is I'll give a quick introduction to the speakers and the companies, and then I'll hand over to Dr. Robert Blum for a short presentation, mostly focused on their technology. He will then introduce Dr. Felipe Della Lucha, who will be giving a short demo and showing how you can incorporate these technologies, almost today into your flows if you're interested. And then finally, there'll be a Q&A section moderated by Dr. Kevin McCumber. Very briefly, I'll introduce Luceda as the host of this webinar. If you're not familiar already, we're an EDA company, so we're a software company based out of Belgium, but with offices globally. We've been around for about 12, 13 years now, and our mission throughout that whole time has remained unchanged, which is to support photonic designers in their product development. We have the slogan that we like to use a lot, which is to help photonic IC designers enjoy the same first time right experience as electronic IC designers. What we mean by this is that in kind of the ASIC teams, they can run all their simulations, verifications, they can build designs, they can tape out with a very high degree of confidence that their design will work. In photonics, that's just not the case today. That's something that we're still trying to march towards. Um, and many of the ways we do that are on showcase throughout this webinar today. PDKs, for example, adding verified components, working with trusted partners. All of these are how we try and advance the PIC ecosystem. Um, then the final slide on Luceda, very briefly, we have a suite of tools covering everything from sort of photonic layout, design, simulation, verification, data analysis. We also have links with partner softwares like Flex Compute and Ansys, as well as Cadence. And we have a whole suite of PDKs covering, I think, about 40 different foundries. So if any of that is interesting to you, please reach out to us afterwards. I'll then introduce Spark. Spark Photonics are our partners in North America. They're also a design house. So as you can see here, they deliver technical services. They provide support and sales for our software. They also develop PIC kits, which can be a really great way for a company to start trying out like a small photonic system without having to commit to their own MPW or tape out. And you'll meet Kevin in the Q&A at the end. And then final slide for me now. It's my great pleasure to introduce Lightwave Logic. As I mentioned, today we have Dr. Robert Blum, who is a Senior Vice President of Sales and Marketing over at Lightwave Logic. He's an industry veteran. He's previously been the head of Silicon Photonics strategy at Intel Foundry Services. He's led the Silicon Photonics platform business at Applied Materials. So he knows the ecosystem, and I think he's going to give us a great show in a little bit. He'll be joined today by Dr. Felipe Della Lucha, who's an expert in modulator design. He's led many tape outs and has done a lot of the design work for some of the devices we'll see today, including running the tape out that some of the results and designs we'll be using are based on.
Couldn't be any better at home. Everything's working.
So without any further delays then, I'd like to invite Robert to share his screen and introduce Lightwave Logic more formally, to explain the company and their mission, as well as explaining why their technology is so exciting and why we're all gathered here today to talk about it.
Excellent. Thanks so much, Matt. Let me just double check here. So this should work. Very good. Yeah, very excited to be here. Obviously, at Lightwave Logic, we're really enabling, the next generation of devices using our electro-optic polymers to enhance silicon photonics. So we have a few slides for you here today. What I'm going to do is give an overview, and then Felipe is going to do a live demonstration of the PDK that we worked on together. I'm just trying to get my window here out of the way so I can actually move my slides. 1 second. It's kind of funny here. Minimize this here. Okay, good. So a little bit about Lightwave Logic. So we're a public company based in Denver or in Englewood, Colorado. I'm in the office right now. As of end of March of this year, we were 40 people, but we're hiring quite a lot. So we've grown quite significantly since then. So if you're interested, we always have a bunch of job openings posted on our website. So please apply there or reach out to me if you want. There's been significant investment over the years, more than $100 million invested in R&D. We have about $100 million in cash also. So, really well positioned for this next wave of AI. We have recently shown that our materials are very reliable. In fact, Manoj, our director of reliability, and I did a sort of a short webinar a couple of weeks ago and presented some of those results where we show more than 2,000 hours of damp heat in our devices. We have a fully domestic supply chain, so the polymer is manufactured here and synthesized here. And we have a very broad product portfolio, 67 granted patents and many more pending. Our business model is really around licensing the IP, enabling the foundries and the design houses really to make enhanced silicon photonics chips using our material to get to high speed, very low drive voltage modulators. One of the things that I'm personally very excited about is really the silicon photonics momentum that we're seeing. So when we launched our first product, our first silicon photonics product at Intel in 2016, the total transceiver market was about $5 billion, and the silicon photonics portion was minuscule, really. And 5 years later, in 2021, what is shown here on that slide, the transceiver market was about $11 billion, and about a quarter, less than a quarter, was silicon photonics. So picking up some momentum. This year, we're really seeing the cut over where silicon photonics is more than half of the transceiver market. So about $20 billion in transceiver sales is based on silicon photonics today. And the market forecast shows that this will grow to more than 70% by the end of this decade. So very exciting times for silicon photonics. And this is really the platform that we're leveraging. And obviously, silicon photonics is great because it's wafer level manufacturing. It leverages all the goodness that CMOS and wafer level manufacturing gives you, but it obviously has some limitations in terms of performance. And so when you look at what is needed for some of these AI clusters, they're very much limited by the connectivity, and you're really looking for high speed or advanced modulators that can integrate very tightly, that have high bandwidth, but also very low drive voltage, low power consumption, low insertion loss, and high reliability. And so there's a few opportunities to basically enhance silicon photonics. And if you look at the two main options, one is you can use inorganic electro-optic materials, such as thin film lithium niobate or barium titanate or similar materials that are largely not really compatible with silicon photonics foundries, but you can add them afterwards. Or you can use organic electro-optic materials like the silicon organic hybrid modulators that we're going to talk about today. And one of the big advantages is that it's basically a material that is compatible with silicon photonics foundries. You can integrate it through spin coating, just like a photoresist. So foundries are very familiar with that material and the deposition methods. And also the electro-optic coefficient is much, much higher than those of the inorganic materials, right? So you can make much more compact modulators than you could with some of these inorganic materials like TFLN. So perkinamine is our chromophores, and they're dipolar molecules that we design and synthesize here in-house, and they're really enabling us to get to these high figures of merit. And if you look at the fundamental effect, you basically have a dipole molecule that in its ground state is already polarized. And then when you apply an electric field, the electron cloud moves over. So you're basically polarizing the molecule. And because you're only moving electrons around, this is essentially instantaneous. So you're not limited by carrier mobility or other effects that limit the performance of other modulator technologies. So for all practical purposes, the bandwidth of the material itself is essentially unlimited for the applications that we're looking for. And the main application or the device implementation that that you see is basically in a slot modulator structure, where you have a slot in your silicon waveguide that you etch. And again, this is a cartoon, and we're going to go into more details in the later slides, but I just wanted to introduce the concept here. So in essence, you etch a slot into your silicon modulator, and then you backfill it with polymer, so that you end up with a hybrid mode where the mode is in the silicon and in the polymer, and you're essentially only limited by the RC constant here. And so you're making these Mach-Zehnder modulators as an example, even though you can make ring modulators as well. But for these Mach-Zehnder modulators, you basically have two arms that are both filled with polymer. And then what is key is that you encapsulate it, because you have to protect the material from oxygen to prevent degradation, and particular photooxidation. So if you're interested in the reliability aspect, I would refer you to the presentation that we have on the website, and the webinar that we recently recorded. There's a lot of information for you there as well. And if you're interested more into the company, we just released actually a new investor presentation that's also referenced on these slides here. So, but the key part for us is we're really combining the maturity of silicon photonics with the very strong electro-optic response of these polymers, creating these silicon organic hybrid devices for really wafer scale photonic integrated circuits, and leveraging everything that's good about silicon photonics, and enhancing it with the electro-optic polymers, right? So it's really key for the scalability, because when you look at what the hyperscalers need, it's really millions and millions of devices, and for that you need a mature, scalable technology. One of the key parts is how to deposit that. So basically, the foundries have to etch these slots in the waveguides. They have to open up the oxide so that the slot becomes accessible. And then we deposit an underlayer and the actual polymer down into the slot. We then essentially remove it where we don't need it. And then we deposit the encapsulation, and then again, subsequently, we remove the encapsulation where we don't need it. So that's the last step. So it's a pretty simplified, pretty simple, and also simplified process that I'm showing here. There's obviously a few more steps, but all the tools, all the processes are standard to CMOS foundries. So it's really very straightforward to implement these deposition steps, the spin coating, and the encapsulation processes in the foundry. We use basically atomic layer deposition for the encapsulation, and for some of these other layers. So all standard tools that are now, or all tools that are now standard in the foundries. And so if you look at some of the structures that we have produced in the past, again, this is just to show you what it looks like in principle, but you can see, if you look on the bottom right, you basically see the electro-optic polymers filled into the slot. And what is interesting here is basically we don't have a PN junction. It's just N-doped silicon on both sides. And you basically, have that to be able to apply to get the electrical field to the slot. But then the mode is really in the silicon and in the EO polymer that is in that slot. And so if you look, I think now is a good time to talk about the PDK. So if you look at the overall Mach-Zehnder interferometer structure, you basically need a few different elements that again, we're going to walk you through some of the circuit design around it. But the key part obviously here is well, let me maybe start at the bottom. At the bottom, where you have just a regular edge coupler or grading coupler, which is just part of the standard Photonics PDK. Then you have, again, the standard power splitter that is also part of the foundry PDK. So this is a standard 1x2 splitter, for example, here. But then what you need to do is you need to convert the mode from the ridge to sort of a ridge slot waveguide. And then after that, you want to convert it from that ridge slot waveguide to a rib slot waveguide, right, where you have a real rib. So there's a few mode converters, and then at the very top, basically in the middle of that, in the cross section across the Marsender section, you basically have the phase shifter, where you have the electro-optic polymer, which is inside this slot, and obviously you have the silicon with different low doping levels, from very highly doped, close to the metal, all the way to very lightly doped, when you're close to the mode, close to the slot. So that, this is obviously the key part of the phase shifter. And these building blocks are part of the PDK that we have. So if you, for example, look at this mode converter, if you start on the top right, you have the rich waveguide, which is in silicon, and again you have to transition that to this rich slot waveguide in the middle, where you have a little bit of a hybrid mode, and then eventually it transitions to that rib slot waveguide, where you have basically this slab that is kind of containing the mode, and then obviously the slot section, which is really critical. So those transitions have to be adiabatic to minimize losses. You obviously want to have them as short as possible, because you don't want to spend a huge part of your modulator length on those tapers. But again, this is key. Key for good performance is obviously these taper sections, and they will vary from foundry to foundry, because again, each foundry has slightly different geometries that they're able to produce, or that are part of the regular PDK. And then on the phase modulator section, this is where it becomes very, very interesting. So again, as I mentioned before, we're basically RC limited. So we want to, if you look at the frequency, you want to have an as low R and as low C as possible to get to high frequency. So obviously you want to, in a way, you want to reduce the doping, but then obviously there's a bunch of trade-offs, right? So if you have high doping, you will also get higher losses, because the mode will start to see the doping in your slot, so you have to trade that off. Similarly for the slot, if you want if you make the slot too narrow, then you have those trade-offs basically with your VPL and also with your frequency. So there's a few different trade-offs, and so the slot width, the rail width, the doping, the slab thickness, all of these are part of the trade-offs that you have to work with. But it's pretty straightforward in a way, but obviously you have to implement it for a specific foundry and really optimize the doping, and the transition from a highly doped N++ doping to the low doping closer to the mode is very, very critical. And so, to give you some examples of the expected bandwidth, for example, here for different lengths. So, for example, if we make quite a short modulator, 250 micron long on the left-hand side, you see here we have a 3 dB electro-optic bandwidth of about 138 gigahertz in this simulation. And as you go to longer, as you go to longer modulators, for example, on the one on the very right, would be 1 millimeter in length, so 1,000 micron length. Those show a 3 dB bandwidth of about 76 gigahertz. But also what is very nice with these types of modulators is that the frequency, there's no rapid roll-off in the frequency, so it's quite linear. So for example, your 6 dB point is around 135 gigahertz or so. So this is very much workable for a lot of applications. And our VPL, which I didn't put on this slide here, is less than 1 volt millimeter. So for these devices here on the right, for example, you have drive voltages that are less than 1 volt peak to peak or lower. So this is quite quite advantageous in terms of performance. Basically, you can get very compact modulators, sub-millimeter, with bandwidth above 100, 110 gigahertz or higher, as I showed here, with very low drive voltages. So I think this is all I wanted to talk about in my portion. Again, we'll have a Q&A later, but let me hand it over to Felipe, and Felipe will go into his live demonstration.
Okay, thank you, Robert. So hi, everyone. So today I want to show you a library that we've built using SilTerra's silicon photonic platform, PDK. Not just the static layouts, but I recorded a video showing how to bring components together to make a final device. Everything is written in IPKISS, so we script components and regenerate them on demand. So I'm going to walk you through this in a bottom-up way, starting from a slot waveguide, which is the core electro-optic element and the basic building block of the component, and building up through the phase shifter test structures and for one wafer measurement, and finally in a complete MZI. So each step reuses the step before. So you see the hierarchy come together in K layout. So Robert, we can start the video now, and I can show you guys a little. So on the left, yeah, we have the library of our components that we design. We have a bunch of them, and the most basic one is the trace that I'm showing there. And the trace is basically a cross section. And what we do, we import the IPKISS in the SilTerra PDK library and our library of components, the trace and the slot waveguide. We set the segment length of this waveguide, for instance, 1 millimeter, and we can set some parameters of this waveguide, such as the slot width, the rail width, the doping profile, and the oxide open window that you're going to have in your slot waveguide. And then you just instantiate the component like shown below. And then once you run the code, you can either open that in IPKISS visualizer. I think the video stopped, Robert.
Sorry about that.
Yeah, so you can see here just a straight segment of the slot waveguide. You can see that in IPKISS visualizer. You can also use K layout to check it out. So you can see the numbers that we used in the parameters, such as the oxide open window that we put 20 microns wide in our example. This is the actual region where you etch the oxide and you deposit the yield polymer to make your device. And you also can, it's also parameterized the rail width and the slot width that we're going to use in the waveguide. So in this case here, we use 200 nanometers for each. And we also have the doping profile parameterized. I have 2 microns and 5 microns for low doping and intermediary dopings. And the length, like I showed before, 1 millimeter, for instance, you can have shorter than that, that Robert showed in the simulations. So this is the basic building block. From that, you can start increasing the hierarchy, such as making a phase shifter. So the same way that we did before, we just import the SilTerra PDK in the phase shifter component from our library. And you can set the active length the same way that we did before. We instantiate the cross section in the phase shifter. We use the same cross section that we used before, that I'm showing here, the active length. And we can also, and it's also parameterized the metal width that we're going to use in the electrodes and the taper of the metals that we're using. So once you run your code, you can check out how the phase shifter starts to look like. So you have the oxide open window, the same one that we showed in the slot waveguide. We have the input and optical input and output on the top and the bottom, which are the mode converters. And we have the metal for the electrodes, 20 micron wide, like I showed in the parameter configurations. And the taper for that metal 10 micron long, we can also extend or make it shorter depending on your design. So this is the base, the second level in the hierarchy. We can also add bond pads to that design. So we also have a component there in which we include the phase shifter with the bond pads that I'm showing there. The same thing, we pick a an active length. We use the same cross section that we have used before, the same phase shifter, and now we have some bond pads. The bond pads that we used are imported from the SilTerra's PDK. So we just retrieve those. We can also set the bond pad dimensions, how wide they are, and the spacing of the wires that we're going to use to route them. And then once you run it, you see the bond pads and the routing of the metals. So very simple and straightforward. You have the 80 micron bond pads in the full metal inputs and outputs port. So here, then for the next step, we can include the optics inputs and outputs. So we can add the fiber arrays and the grating couplers that we also import from SilTerra's PDK. So you also set the active length that you want. In this case here, we use the same parameters from the waveguide, the same parameters for the phase shifter. Obviously, you could change that, the bond pads, and then you can also set the fiber array that you're going to use. In this case here, it's 4 grating couplers. We import that from the PDK with that command there. The separation between the grating couplers, depending on your test measurement setup. So in this case here, I'm using 127 micron. And then you can just make a test key for that component, and you can run it. And when you check it in KLayout or in the visualizer, then you can see the full phase shifter with the grating couplers, the fiber arrays, and the bond pads, the routing from the input to the output of the phase shifter through the mode converters, and the grating, and lastly the grating coupler. So with this, you can do the polling in your polymer, and you can also apply voltage and do some slow speed modulation in that case to extract parameters from your components such as VPI and loss. Last but not least, I have here a quick demonstration of how you would make an MZI. So the same way you import the SilTerra PDK and the library of components that we have there. So we have the traces, and also an MZM from our library. That MZM, in that case, there's no metal on it. It's just the phase shifters. But the components from the foundry, such as the MMIs, they are present in that. So we can, the same way we can set the parameters for the waveguide. And once we hit the run button, we can see the MZI with the 2 arms of the Mach-Zehnder. So you have on the top there, it could be your input. So you have the MMI, you split the waveguide in 2. You have the mode converters for each side of the arms. You have the phase shifters for both sides. And then you have the output mode converters, and you combine them back using the foundry MMI. So from that, we also have the component with the RF electrodes, which you can build on top of this, the same way that we've done with the phase shifter. So I wanted to show how simple that is. It's 2 lines of code. You can make your a full device. And but the key takeaway here is that every level of this hierarchy, from the raw slot cross section to the complete RF-driven modulator, everything is parameterized and generated in IPKISS. So you can regenerate any variant or DOE configuration on demand, rather than making hand drawing layouts or taking a long time. So it's pretty simple, very straightforward to use.
Great. Thanks, Felipe. And yeah, if you want to reach out directly to me or Felipe, I can relay that information. Here's my email as well. I think I'll bring it back to Matt. I think we're gonna share something here and so that we can go into a Q&A.
Yeah, let's jump into the Q&A. Thank you so much, Robert, Felipe, for the presentation. It was great. See a couple of questions here in the chat. I'm actually going to put these folks on the spot and ask them if they wouldn't mind coming off mute and asking these questions live. The first one was our friend Ahmad from over at OptiWave. Ahmad, would you mind posing your questions to the presenters?
Sure. Okay. Thanks for the presentation. It's nice. Question is about the bandwidth of, like you showed. I asked the question before you showed the slide about the bandwidth. Okay. So with the bandwidth right now, this is simulation you mentioned though, right? Experimentally, how much is the bandwidth did you get basically for these devices?
Right. Yeah, so some of the results we had shown in the past, they're more than 2 years old, right? So we've seen more than 110 gigahertz in the actual devices. And we now have more data coming, so we'll see where the measured bandwidth lands. But yeah, simulation obviously shows 135 gigahertz or much higher even for shorter devices, right? So it depends a little bit on the length. But for the 250 micron device, we're expecting about 135 gigahertz. Again, it's RC limited, so and it varies a little bit by foundry also in terms of what the capabilities are there.
And the other question is about the insertion loss of the device, like for this short length, how much was like the simulation? You didn't show that result. You
We didn't
talked
show
about
that.
it, but yeah.
Yeah, I mean, obviously it gets a little bit sensitive because of also the foundry processing capabilities and the roughnesses there. So the main contribution is some of the surface roughness on those slots, right? And we have the tapers down to less than half a dB, the adiabatic transitions to that slot, and so then it's mostly scattering losses. But again, we're going into specifics, we probably want to discuss it under NDA because it involves also the foundries.
But can you give a rough number right now or no?
It's a couple of dB for the modulator. Yeah.
Okay. The other question I put in the chat, I'm sure, Kevin, you allow me to ask it so I don't come back again.
Please go ahead.
Is about the bidirectionality of the device. Is it possible like to do the modulation east to west and west to east as well on the device, or there is limitations?
I think it should. Felipe, do you want to comment on that? I mean,
Yeah, it depends on your design, but it should be okay to have it bidirectional. Obviously, if you have a differential design, a terminated one, then it's only one 8-way. Same thing for a single-ended device. But depending on your design, you can make it bidirectional.
Okay. And there is no bandwidth limitation in that sense. You
No,
don't
well,
expect any bandwidth limitations
no,
directionality.
no.
Sorry.
In terms of the polymer itself, the bandwidth there's no limit, at least for the current state, we can measure it. So it's totally RC limited by the doping profile that the foundry can make. And it's a trade-off between the optical loss and the bandwidth that you're going to incur. Because of the higher the doping, the better the bandwidth, but the higher the loss as well. So
Okay.
there's always this trade-off. Yeah.
Perfect. Thank you.
Great. Thanks, Ahmad. I also wanted to just thank our friends over at SilTerra as well for allowing us to show some of these examples with you all today. I appreciate their being open about that as much as we can be. Let's see. Next on the list, we had Javier Champagne from CEA Leti. Javier, would you mind posing your question here to the presenters? If he's still online. If not, I will do it for him. He asks, how does the carrier mobility in lower dope silicon near the waveguide not become a limiting factor of the modulator's bandwidth?
Yeah, well, I think that's again part of the trade-offs, right? And again, I can have Felipe comment as well, right? But obviously, um, if you want to get the resistance way down, then you dope very highly, and then you get high losses because the mode sees the dopant, right? And so it's mostly a trade-off, right? I wouldn't say that, but because it's not a PN junction, we're not interested in the carrier mobility like you would be in a traditional silicon modulator, right? So it's just an RC limitation, and so the bandwidth comes from the EO polymer, right? And the dopant is just to bring in the electrical signal essentially. So I don't know, Felipe, if I missed something.
No, I think
That's it,
yeah,
Mhm.
that's it.
Hello, hello. This is Xavier. I'm the one who asked the question. I'm sorry, I didn't unmute earlier. I couldn't figure out how to do that.
Okay.
So thank you for taking my question and answering very clearly. I think the bit that I had wrong in mind was that uh, I come from I have a PN junction background in modulation, so I think
Right.
that's what threw me off. And you've answered the
Yeah.
question very well. Thank you.
Okay. Thanks, Xavier.
That's part of why we run these webinars, is to expose us all to these other very interesting modulation schemes. Let's see. The next question in the chat here was from our friend Sanawar over at University of North Dakota. Asked if we can share the slides. We will be posting this to the Luceda Photonics YouTube channel after the event. So please go on out there and you can relive all the glory from the presentation at your leisure.
Yeah, thank you.
Absolutely.
Good.
I'll open it up if anybody else has other questions they'd like to pose.
I have a
Hello?
question I'd like to pose. Considering the efficiency, you showed us a Mach Zehnder with 250 microns length,
Mhm.
and I suppose that you would. What is the efficiency in phase shift that you expect in terms of index change per volt? Are we
Right.
talking about 10 to the -4, 10 to the -3
Yeah.
index change per voltage?
Right. So it's basically it's in that area, right? I mean, so the electro-optic constant, the R33, is about 200 picometers per volt, and the effective the V pi L that we're seeing. So V pi times length of the active region is less than 1 volt millimeter, right? So for a 250 micron long device, the V pi is about three-ish volts, 3.5 to 3.5 volts or so, right? So that's kind of the area that's sort of the design space that you're operating in.
Okay, thank you.
Mhm. And the 200 is essentially almost an order of magnitude larger than what you would get in lithium niobate, right? Lithium niobate is about 30, so we're 7 or more higher. And again, there are some trade-offs. You can get to higher R33 as well, but we think the 200 is actually it's a good number for sort of a production type spec.
Hello?
Hey, Siddhartha.
Yeah. So I have a question regarding the MZM design. So there is a power splitter, and that splits and connected to the two waveguides, the slot waveguide. So in the power splitter, the light travels in silicon, and in the slot waveguide, it travels in the polymer. So, uh, so how does that like? Uh, so the light route converts from silicon to polymer like at the abrupt junction, or it is like some
Yeah.
there is a continuous change.
Yeah,
I just want.
Yeah, so I'll take the blame for not explaining it well. And again, I'm also happy to email you the slides afterwards if you want to ping me separately. But basically, yes, you have it in the silicon. So the regular 1x2 splitter, for example, is part of the regular silicon photonics PDK that the foundry will have. And then we have these adiabatic converters, basically two sections where we converted very gradually to this slot wave, eventually to that slot waveguide, where the mode is, yes, in the polymer, but also in the silicon, right? So it's a hybrid mode. It's kind of looks a little bit, complex because again, you have these high index regions in the silicon, and then in the middle, the polymer index is around 1.9, say, for discussion purposes. So it's lower than the silicon, which is around 3.4. So you have this mode, but because of the slot being narrow, the mode is basically in the polymer, or a large portion of the mode is in the polymer, right? So the key here is that you have, and that's part of our PDK, and it's but we black boxed it for this demonstration and for the PDK. But these mode converters are obviously quite important to get the conversion right, so that you have low losses, less than half a dB typically, and that they're still very compact. So but in essence, it's just a simple adiabatic converter to get it from that ridge waveguide to the slot waveguide and then back again.
Thank you.
Okay.
Other questions?
Kevin, we can also just wrap it up on time.
Well, I'll pose one last one to you. Let's say my company is interested in taping out with your EO polymers at SilTerra. What is my first step to do that?
I would say the first step would be to reach out to us or to Luceda, obviously, and discuss how we best work together. We have multiple tape outs, or we have a tape out in progress now. We have multiple tape outs coming up, right? So there's opportunities to put some of the your designs on our tape out, for example, or if you want to do a dedicated run, we're happy to be there to support you. Again, the PDK is available, but we expect most customers to want to get some amount of hand holding, so we're happy to support as needed.
That's great. Thanks, Robert. So for anybody who's interested in getting in touch, please reach out to Luceda directly through the emails you've received about the webinar, and we'll be happy to get you in touch with the folks at Lightwave Logic, or you can reach out directly if you're already in touch. I want to thank Lightwave Logic as our featured presenter for this first webinar in our Advanced Materials for Modulation series. We will be having additional sessions of this series in the upcoming weeks, so please stay tuned. You can check out the Luceda Photonics LinkedIn page for more posts about this, as well as the Luceda Photonics event page on their website. Look forward to seeing you there. Thanks everybody for joining.